All right, so I'm in the voice channel. YouTube has started, so the recording of the live stream has started already. Um, Class is going to start in about 3-4 minutes. If you have questions, I can try to answer some of the questions before class starts. So go ahead if you do have questions. And right now would be a good time to put some entries into the daily log. Okay, so this way you don't forget to do it, because we are still kind of waiting for the whole class to come in. Because the daily log is what I use to quote unquote take a roll. I cannot keep track of people who are in the general channel. So the best way for me to take roll is really to look at the timestamp of the document shared with you as your daily log. So use that. All right. So there doesn't seem to be a whole lot of questions so far, which is good, I guess. What we'll do today is the first thing I'll do is to create the circuit that that you have to do, that you have to create in your lab. So I'm gonna show you guys, exactly how to do it, unless people. Oh, you guys cannot hear me? That's interesting. Okay, so that may be a specific issue with only certain people. Okay. All right. Thank you for the confirmation. Yep. Click on the gearbox in user settings. And also, yes, also click on the general voice channel in order to be a part of the channel. Okay. 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 I can take a screenshot of what people should be seeing. So let me take a screenshot here. All right, I think it's about time. So we are 24 seconds past 9 o'clock. I am going to get started here. If anyone is having an issue live getting the audio part to work in Discord, the alternative is to watch the YouTube. It's going to be a little bit behind the Discord live stream, just because YouTube has a longer lag time. But it is an option in case your Discord is not working. All right. So what we'll do is we're gonna quickly go over the lab that you have to do yesterday, and then we'll move on to today's topics. So let me go to my Logisim screen, which I thought I had, but I might have closed it accidentally. Yep, probably closed it already. Let me look into my taskbars. Nope, I don't see it. Alright, so that's okay. We'll go ahead and just start it over. And I'm going through all my terminal windows to find the right one. Okay, there we go. Alright, so there we have it. This is the terminal window. So for the most part, inside the lab itself, there's already a video to show you how to do this. So I'm doing this, here in case there are people who want to ask questions interactively. So we'll just kind of quickly go over this. First of all, we need an input pin that is 8-bit wide. So it is technically called a pin, even though it is wider than just 1 bit. Okay, and then the output is another 8-bit pin, but that's an output pin. Oops, I have to change it to 8. So the only reason why we have 8 bits in and 8 bits out when we only need 2 bits in and 1 bit out is so that the circuitry will hook up to the tester without any additional circuitry. And it is also a good way for you guys to practice how to use a splitter. So in the case of a splitter, there are 2 specific ends. This end of the splitter is the merged end, and this is or combined end of the splitter, and this end here is the split end of a splitter. So there are several attributes to a splitter. I explained this in the other video already. The bit width is independent to the fan out. So the bit width has to match. So this port over here for the input pin is 8-bit wide. It has to match the number of bits of the combined end of a splitter, which is now 8-bit wide. But of all the 8 bits, we only need the first 2. So bit 0 is going to be the top, which is this wire over here, and then bit 1 is going to be the bottom one. Everything else are not going to be connected. So you can just turn them all off. There are several ways to do this. You can also have a fan out of 8 and just do not connect the split end that is not useful to us. Okay, but that just looks ugly, and I personally prefer to do it this way. So this way there's no chance that I can accidentally connect something that is not supposed to be connected. And then we got power. So power is basically quote unquote the source of 1. I believe you can interchange power and ground with 0 and 1, and I think the circuit will still work. But in this particular case, in this very, very specific case, a transistor is a physical device, so or as close to a physical device in Logisim as possible. So that's why we are kind of do it this way. With a p-type transistor, the first thing we want to do is to rotate it. So we want it to face south, like so, for at least one of the 2 p-type transistors. So we put one over here, Control D, duplicate, and put one over here. And because we want the gate position to be on the other side, so we flip the gate location without changing the rotation of the device itself. And then we Control D, duplicate again. And this time we want to make 2 N-channel MOSFETs. So we'll turn it into an N-type, and then the heading has to head north, because when an N-type transistor, the source has to go to the lower voltage, which is ground. And then we have another one here. Okay. And if we flip the other one in terms of the gate position, so this way it's easier to hook up the 2 gates here, and then the 2 gates over here. And then the output pin also needs its own splitter, so you can copy and paste the splitter, because it's not going to help a whole lot, because when we change the fan out to 1, Logisim will basically reassign all the bits to the one single split end, which is exactly the opposite of what I wanted to do, because I just want to have one single bit corresponding to the split end and not all 8. So this is rather tedious. And in today's lab, you're going to have to use a lot of these splitters. So my recommendation is to use the duplicate function as much as possible, so you don't have to redo this all the time. And then we are going to change the phasing from east to west, because we want the merged end oh, okay, I did not intend to draw a trace. I intend to move this the splitter. Okay, so we'll line up everything kind of a little bit nicely like that, and um, now we make all the connections. It is really important to observe the direction of the field of the transistors. It has to go from source to drain. And for a p-type transistor, the source has to connect to the higher voltage. And for an n-type transistor, the source has to go to the lower voltage, which in this case is the ground symbol. So we'll hook it up like this. And then the two n-type transistors are connected in series, whereas the two p-type transistors are connected in parallel. Okay, so in case you have taken a physics class already, or in case you have taken a circuits class, these are the terminology to describe the topology of how things are connected. So we'll just randomly pick the first, or bit 0, to connect to this particular p-type MOSFET transistor, and then the other end to connect to this one, and then the bit 1 is going to connect to the gate of the other p transistor, as well as the other n transistor. So I'm just gonna, so this looks a little bit different compared to what the lab has. Oh, okay. Let me get rid of that. That's really just cosmetics. I mean, it doesn't really change the logical connections. So right now we have the circuit already done. Only bit 0 and bit 1 of the input pin would actually affect the output. So right now we have 0, 0. And this is also, where we are going to begin the discussion of today's topic, which is, how this circuit behaves like a NAND gate, a negated AND gate. So we can see how the two inputs, okay, particularly, just bit 0 and bit 1, they're both zeros right now, but the output is a 1. So that is consistent with a NAND gate or NAND operator, because 0 and 0 is a 0, but the negated 0 is a 1. So that's why it is consistent. If at least one of these two bits is a 0, the output will continue to be a 1 because it is a NAND gate. So if I turn this one into a 1, you can see the highlight is changed a little bit, but you can also see how the output is still a 1 in this case. And that's not really surprising, because if at least one of the two inputs is a 0, then one of the two p-type transistors is going to be connecting the drain to the source, and as a result, the output pin is connected to the high voltage, which is registered as a 1. And for the same reason, if at least one of the two input pins is a 0, then at least one of these two N transistors is going to be off, or it is not connecting. Because the N transistors are connected in series, so if at least one of them is not connected, then there's no path from the output pin to ground, and as a result, that's the only connection for the output pin is to connect to 1, and that's why it's still registered as a 1. So we'll go ahead and flip this, put this one as a 1, and you can see how the output is still a 1. The only time the output is going to go from a 1 to a 0 is when we have both inputs being 1s. So you can see how when we have the input being 1, 1, the output is now a 0. That's because when the input is 1, 1, both of the p transistors are now off. There's no path for the output pin to connect to the high voltage. On the other hand, because both of these are 1s, both of the N transistors are now connecting. So now, even though we have a series circuit for the N transistors, but because both of them are connecting, so we do have a path from the output pin through the two N-type transistors to ground, which is basically 0. So that's why, but when you look at this, 1 and 1 is a 1, but the negated state of that is a 0. And this is why this particular circuit, using only 4 transistors, is a very simple implementation of the Nand Gate, N-A-N-D, which is negated AND gate. So do we have any questions about this before we move on? So this is both a demonstration of how to get your lab done, from yesterday, and also a continuation of the topic that we have already started from yesterday. Okay, there are no questions so far. All right, so if there are no questions, then we'll go ahead and just kind of take a look at the appearance of the circuit. So if you look at this, okay, let me click it here again. If you look at this as the definition of a function, this over here is the prototype of a function. In other words, if I want to use this circuit in a larger circuitry, how do I interface with the circuit? So the position of the pins is really important. Now in this case it's not as important because we only got one input pin and we only got one output pin. So there's no source of confusion. If you click on one pin, you can see how the picture-in-picture actually, okay, my own picture is over the picture-in-picture, so let me move that, okay. And then go back here. So now you can see, let's see here. There we go. So you can see how in the picture-in-picture, whatever pin you have selected is highlighted in the pip. And same thing for the output. The output is a little bit more difficult because it also has the orientation marker. But now you can definitely see, how to double check to make sure that, the pin that you see on the quote-unquote packaging or the appearance does correspond to the intended pin that you want that to connect to in the implementation of the circuit. So do we have any questions up to this point about Logisim or about the NAND 2 gate that I have just created? All right. So I'm not seeing any questions. I'm not hearing any questions either. So I'm going to move forward. Going back to the notes. So now we go back to the browser. Okay, there we go. That's basically what you need to turn in. So going back to Logisim, you just have to save the file, as NAND2. The extension of CIRC is automatically appended to the name, so you don't have to type that in, and then you just turn it in, in the lab. And what I'm going to do with that, okay, I kind of explain it in a different link, is I have a tester circuit. So the tester circuit already has a correct implementation of the NAND 2 gate, but what I'll do is I'm going to generate test cases, and I will plug your circuit in place of the reference circuit, and then test and then use the output and compare to the output of the reference circuit. If they are the same, if your circuit gives me exactly the same output, then it is 100%, okay, it's correct. If not, well, then I have to kind of decide what to do with it, because if it doesn't work in all the cases, obviously that's going to be a 0. So the only tricky case is, what if it works in some cases and not in other cases? So I have to kind of decide on how to assign points to that portion of the lab. All right. So are there any questions? I'm not seeing anything from Discord. All right. So I'm going to move this Logisim window aside here, so that we can continue with the module that we were on yesterday. So we have basically gone over a lot of the module already, because I just used about 15 minutes to kind of go over this circuit, and also I briefly explained how the circuit works. In other words, how does the input XY influence the state of the output? We just talked about that as I was exercising the pins inside Logisim. So basically, technically, okay, we are done all the way up to here. Do we have any questions? Okay, we got someone typing, so I'm gonna wait for that question. Or do we not have a question? I cannot tell because um, Murtaza, started typing and then stopped. All right, so I'll address the question when it appears in Discord. So the circuitry that we just looked at, oh, there we go. When we save it, how can we open it again? So when you open a Logisim circuit, what you do is you start Logisim first, then you open the file from inside Logisim. I can show you that. Okay, I'm going to close. Okay, okay, you cannot see this. I will move this into the portion of the screen that you can see. There we go. So you just go ahead and save it first. Okay, so I don't care where I save this particular one because I got it done already in a different different file. So I'm gonna save this one under the temp folder, which is a Linux and Unix kind of thing. So save. There we go. So what you do is I'm just gonna pretend that this is the next day. I come in and go like, oh, I want to work on this circuit again. What do I do? So what I need to do is on the command line, I need to run the java-jar command again. So I'll get it started. Okay. So now Logisim has started with a blank circuitry. And then from inside Logisim, I go to File. I can usually go to Open Recent to find the file that I have recently worked on, and I think it keeps track of like 10 of those. Now, if none of these is what I want to open, then I can just click Open. Then I can navigate to the folder where the file is located. But typically, if you're working on a particular design and you just worked on it previously, you just go to Open Recent and reopen the file. So I hope that answered the question. All right. So what we have here is called a Nand gate because it is a negated AND. So the way we denote a Nand gate, or the operation that is associated to what we just did, is W, which is the output, is exclamation point, which in C and C++ is logical NOT, and then X and Y, which is the logical AND between X and Y. So this is in C++ syntax. In mathematical symbol, this kind of like a cliff sign here is negation, and then this kind of like an inverted V symbol is conjunction. Or if you want to spell it out in English, you can also say W is not of, in parentheses, X and Y. So all of these are basically acceptable notations that you can use in this class. All right. Do we have any questions about the Nand gate? Okay, doesn't look like there are any questions. All right. But this is really important, okay? Because at this point, what we have just done is to use physical devices, transistors, okay? We have just used 4 transistors to implement something that performs a logical function, a logical operator that is now implemented in using 4 transistors. Now this is big, okay? I think this is really big because what this means is now we have a connection between a physical device that can influence physical quantities and whatnot that actually performs a logical function. Okay, because NAND 2 is basically a logical function. It is a logical operator. So this is really significant because we have just connected, the physical world, okay, to logical operation, even though it's a very simple one, but we have now made the connection to implement a logical function. So are there any questions about why I think and you probably should think this is significant as well? Any questions? All right, I'm not seeing anything on Discord. Okay, so now the question is, NAND seems really odd, right? Because we don't have a single symbol or single operator that denotes NAND in C or C++ or Java or JavaScript or Python or Perl or PHP or Lisp or Prolog. Okay, no programming language has an operator called NAND. So isn't that really kind of pointless and kind of useless? Okay, that's kind of the question. The NAND operator is often used, mathematicians use the up arrow symbol to denote NAND. Okay, I'm guessing, because the regular AND looks like this, and then the vertical bar is kind of a symbol that says not, okay, negated of. So that's basically what mathematicians use as a single symbol to represent NAND. So now we want to say, well, if we only have NAND as a logical operator, can we use it for other things? Can we use NAND to implement logical operators that we are familiar with? And we got a question here in Discord. For testing, will you require logic notation like these examples? I'm not really sure what the question is asking. If you're talking about testing in the sense of grading your submission, then the answer is no. When I'm grading, I will try to automate it as much as possible. So my script will basically look at your circuit file, and it will substitute your circuit file in place of the reference circuit that I already have for grading purposes, and it will look at the output of Logisim and compare the output corresponding to your submission with the reference design. Or do you mean for exams when you mention testing? That's perfectly okay. Notations, for notation purposes, you can use the C notation, which is fine. And then later on in this class, I will introduce a shorthand so that you're not going to use and, which takes a little bit of time to type to denote conjunction or and. Okay, cool. All right. So 3.4.1 in the notes talks about, well, if I only give you the NAND operator, can we use the NAND operator to implement logical NOT or logical negation? The answer is yes. Okay, in fact, it is very simple. Very simple. The negation of x or not x is really just x NAND x. Oh, you're welcome. It's really just x NAND x. Now, how do we know this works? Well, there are several ways to kind of prove that this works. The best way to do this is a truth table. Okay, I'm not sure how many of you are exposed to the concept of a truth table in your other programming classes. If you're not, it's okay, because we are going to do it here. I'm going to use a text editor in this case because I can type a little bit faster this way. So when you look at the truth table, okay, you have one column or several columns. It depends on how many independent variables do we have. So in this case, we only got one, which is x. And then in the other columns, you evaluate. Let's take a look at the negation of x, okay, which is just the logical NOT of x. And then we look at x NAND x, okay, x NAND x over here. But if you say, but x NAND x is not familiar, I'm not familiar with that operator, it's okay, spell it out as the negation of x and x, like so, okay? Then, because x is a Boolean variable, it can either be false or true. So from here on in this class, I would basically use 0 to represent false, and I would use 1 to represent true. Not false is true. And then over here, we need a little bit more time because we have to say false and false is false, not false is true. And then when x is true, not true is false. Over here, we're going to take a little bit longer. We'll say true and true is true, not true is false. So now, when we look at this truth table, we can see how the second column and the third column have exactly the same values for each row. And that is enough of a proof to show that x NAND x is equivalent to not x, which is what the note is suggesting over here. So do we have any questions about how I just proved that x NAND x is in fact exactly the same thing as not x? All right, there doesn't seem to be any questions. Moving on. Then what about and? Okay, without the negation. Well, since we already know how to do the negation itself, right? And NAND itself is the negated AND, so that means x and y is really the same thing as x NAND y, NAND x NAND y. Now I know it's a little bit hard to spell out, but that's basically what it is. Okay, it makes sense, right? Because x NAND y by itself is the negated AND. So if I negate that with, or if I apply that through a NAND with itself, then I would just negate the negated AND, and then I just get a regular AND back. So are we still doing okay so far? You know, how we establish the equivalency between x NAND y NAND, x NAND y is the same thing as x and y. I cannot wait to read the closed captioning of this part of the video, because I wonder how much Google can pick up, because NAND, N-A-N-D, is really not an English word. So it'll be kind of interesting to see how that got translated. All right, moving on to OR. So OR is a little bit more difficult. So with OR, what we are doing is we first have to translate OR into AND first, and this is called De Morgan's Law, and we are going to use De Morgan's Law a lot, quite a bit in this class. But before we get to the De Morgan's Law, we just have to say, well, are we sure these two are the same? Okay, well, yeah, we do, because double negation cancels out. So x or y is really the same thing as the negation of the negation of x or y. So that part is okay. So now what we're doing is we are taking a look at the negation of x or y, and then we use De Morgan's Law and say that, oh, it really is the same thing as not x and not y. Martin has a question. Can I explain the AND again? Okay. How should I do it? We can do it using a truth table. Okay, so we have x and y. We have two independent variables. So we have the usual x and y, and then we have the x NAND y, and then we have x NAND y, the whole thing. Oops. Oh, where's my cursor? There we go. Oh, you guys cannot see this part. Hold on a second. Move it up here. So now we have x NAND y, NAND x NAND y. Okay. Now, because we have two independent variables, when x is false, y can be false or true. When x is true, y can also be false or true. Okay, so are we still doing okay? Are we doing okay so far of why we got 4 rows in this particular truth table? Because 2 to the power of 2 is 4. X and y, okay, that's pretty easy. We got 0, 0, 0, and then a 1 over here. X NAND y is just the negated version of AND, so we just flip all the zeros to ones. And then we flip the only one into a 0. Are we still doing okay so far with this? Okay. So now we get to here, which is the same thing as the negation of x NAND y, because we already know that from the first truth table here. So now we're flipping all the ones back into zeros, and all the 1 and then only 0 back into a 1. So we got 0, 0, 0, and a 1. So in this truth table, we can see how this column of x and y has exactly the same value as this column here, which is x NAND y NAND x NAND y. So now we have established that the simple x and y, which we are familiar with, is equivalent to the more complex version of spelling out the entire thing, which is x NAND y NAND x NAND y. So that's basically the proof of 3.4.2. Now 3.4.3 can be proven exactly the same way. In other words, if you make a truth table, make one column x or y, make the other column x NAND x NAND y NAND y, okay, then you will find that it really has the same, it's going to do exactly the same thing as x or y. So I'm gonna leave that up to you guys. Okay, I'll give you the template. Okay, I'll be generous in this case. I'll give you the template, and I want you guys to do this on your own. Okay, look at this as one of those ungraded homework assignments. So kind of the same thing over here. Yeah, the truth table is really helpful to understand logic. So now you can look at x or y as one column, and then you look at x NAND x as one, and then now in terms of columns, this one's going to have more because you have y NAND y, and then the last one is x NAND x NAND y NAND y. Woo, there we go. And you kind of have to backfill all the values, so I'm going to clear the values, so that you have the room to fill it in, like so. But doing this once in a while, is really helpful because it really helps to intuitively show you, why two Boolean expressions are equivalent. So I really think that this is a good exercise for you to do. So I'm going to save it first, and I'll call it 2020-0609.txt, and I'll put it into Discord. So when you go to Discord, you will now be able to download that file. Okay, work on the OR truth table. There we go. And I will even pin it. So once I pin it, then it becomes really easy to find because you just go to the top of Discord and you see that little thumbtack thing. Just click on that and all the pinned messages will now be listed under that pin. All right. Shall we move on? All right. So there are no additional questions. So now this is really interesting too. Okay, so we just made the leap from using transistors, which are physical devices, to implement logical operators. Well, I shouldn't say logical operators. A single logical operator, which is really odd. It is called a Nand gate. Okay. But now we have used the Nand gate or the NAND operator to implement the logical or Boolean operators that we are familiar with, okay, which is negation, conjunction, which is and also disjunction, which is or. So, wow, this is really cool because we have already made a connection all the way from transistors, low-level physical devices, to programming concepts, or at least a very small set of programming concepts that you have already learned from CISP300 and also 360. So that should be a little bit exciting because, hey, we are making connections between the new stuff that you're learning to the old stuff that you have already learned. I can see from the lack of posting and voice comment that no one seems to be very excited about this, but I am excited because this is really cool. We have just made a significant connection between the concepts. Oh, great, thank you. It's good to know that people are actually listening and going, yeah, this is really cool. All right, so the last section talks about numbers and values. In other words, okay, Tech, we just talked about how to deal with zeros and ones. Okay, we we represent 0 as quote unquote the low voltage, and we represent a 1 using quote unquote the high voltage. And we have this kind of weird little circuit called a Nand gate that uses 4 transistors. Okay, I'm just moving this up so you can see what I'm talking about, to implement a Nand gate. And then we also know how to use a Nand gate to implement negation, conjunction, and disjunction. What about numbers? What about values? What are we going to do with those? Okay, so this is why we are moving on to the next module. The next module talks about base conversion, and then once we're done with the base conversion, we'll focus on a particular base, which is base 2. When we're dealing with base 2, then we got zeros and ones again. So that means, hey, we can now also use the same standard. A low voltage is a 0, a high voltage is a 1, but then the module after that we'll talk about how about addition. How do we perform addition using just zeros and ones and then logic gates? How do we perform subtraction? Okay, how do we compare numbers? That's basically kind of the next few topics over the next few days of what we'll be talking about. But I do want to give you the context of how this particular concept, these concepts, I should say, connect to the concepts that we'll be talking about in the next few days. So we are now done with physical states, truth, numbers, and computers. And we are moving on to the next one, which is values, numbers, and bases. The lab NAND 2 will be released later today, so when I'm done with the lecture, I will open the lab up for you guys to work on it. This one is actually pretty simple. In some way it is simpler in terms of concepts compared to the first one, because the first one is tedious. There's a lot of little things. You have to learn how to use the command line interface and stuff like that. With this one, it's mostly just conceptual stuff that I have talked about already in the previous 15 minutes or so. So now we are moving on to values, numbers, and bases. The first thing about this module is, what is the difference? What is the difference between a value versus a number? Okay, because these two things seem to be interchangeable. Well, they're actually slightly different things. So if I kind of hold up, a certain number of fingers, okay, so since we are live streaming, you can see, in the little window of me, I'm holding up, a certain number of fingers. Okay, I have to do the mirror image thing because there we go. So this is a value. Okay, this is a value. Okay, and you guys are thinking, well, what is the big deal? There are 4 fingers. Well, that word 4 is a number. In other words, 1 is a concept. Okay, this is a concept, but when we use the word 4, it is not a concept. It is a word for communication. So numbers are really just a representation of a number is a representation of a value, so that we can convey that value to another person or to another computer and so on. So number is kind of like a name. Okay, you're looking at a video, you're looking at my face right now, so that's me, right? A person. Okay, but you can say, but that's tech. Tech is a name. Okay, that name is used to refer to me. So when in a conversation, you can now say, tech classes are really bad. Tech sucks as a professor. Okay, well, that's a reference. Okay, you're using the word tech to refer to a person, and that's me. Okay, but the actual person is me, which may have other names. Okay, I might have other names in other languages. Okay, my father may not call me tacky, and my father may call me something else, right? My wife may call me something else. My kids may call me something else. So we have multiple ways to refer to the same thing, and it works out the same way. There are different numbers to refer to exactly the same value, and that's because we can choose different bases. Now, the base that we are used to is base 10, okay? And to us, base 10 makes sense, right? And that's only because we got how many fingers? We got 10 fingers. That's why we are using base 10. But other than that, base 10 makes no sense whatsoever, okay? Now, I'll explain it later, okay? I'll explain why base 10 is really a bad base to use, okay? Base 8 is good, base 4 is good, base 16 is good, okay? Base 10 is really not that good, okay? Other than the fact that we have 10 fingers. So that's kind of the premise of this entire module. So what we'll do is we are going to move forward here. And what we'll do is we're going to take a look at a number. Okay, this is the number that we are going to look at, which is 16.375. And that's base 10, okay, unless I use a notation to specifically refer to a number in a different base. The default is we are still using base 10. So this is just base 10, it is known as 16.375. Okay, so what can we do about 16.375? I can break it up and say that 16.375 is the sum of 10, 6, the 0.3, the 0.07, and the 0.005. Okay, that's not rocket science, is it? Right? I mean, this is like, wow, come on, Tack. This is the kind of stuff that we learned in elementary school. And then I throw in something else. I go like, well, the 10 can be rewritten as 1 times 10 to the power of 1. The 6 can be rewritten as 6 times 10 to the power of 0. The 0.3 can be rewritten as 3 times 10 to the power of -1. The 0.07 can be rewritten as 7 times 10 to the power of -2. And then the 0.005, excuse me, the 0.005 can be rewritten as 5 times 10 to the power of -3. Okay, wow, this is stuff that we learned in either middle school or high school. What is the big deal? The big deal is there is a pattern to it, okay? So we recognize a pattern. What pattern are we talking about? The pattern is, it has to do with the power of 10 that we multiply by a quantity. 1, 0, -1, -2, -3. What are we multiplying to these powers of 10? The individual digits, the 1, the 6, the 3, the 7, and the 5. So what this means is in a traditional number, okay, in any sane number system, each digit is telling us the quantity of the power to whatever base that we are using. This 1 here is telling us that we have 1 of 10 to the power of 1. This 6 over here is telling us that we have 6 of 10 to the power of 0, 3 of 10 to the power of -1, 7 of 10 to the power of -1, and 5 of 10 to the power of -3. This is nothing new. I certainly hope that this is nothing new, okay? Because this is stuff that we have been using for a long time already by this time. Okay, but when we see a pattern, okay, the next paragraph talks about when we see a pattern, then we can use mathematics, okay, we can use notations to generalize, what we have just observed. So V over here is the value. D0, D1, D -1, those are all digits, okay? D0 refers to the digit that represents the number of 10 to the power of 0. D1 is referring to the digit that tells us how many 10 to the power of 1 do we have. D -1 is telling us is the digit that tells us how many 10 to the power of -1s do we have, and so on. So technically speaking, a number can have an infinite number of digits, okay? Because to the left of this 1 over here, you can kind of imagine that we have a whole bunch of zeros. Okay, we don't have a 10 to the power of 2, we do not have a 10 to the power of 3, we do not have a 10 to the power of 4, and so on. So technically we have an infinite number of zeros to the left hand side, But we also have an infinite number of zeros to the right hand side as well, because we can say that, oh, there are none of 10 to the power of negative 4, there are none of 10 to the power of negative 5, negative 6, negative 7, and so on. So when we want to look at the value of a particular number and we want to make it as general as possible, we can just say that, well, maybe the number has an infinite number of digits. I don't care, okay? Because what the number which is represented by the digits of d subscript I, the value being represented by that particular number is really the summation. This is the sigma notation, which is basically a summation operation of d of I times 10 to the power of I. That is basically how we interpret a number and convert it into the value that the number is representing. So I'm going to stop a little bit here. Okay, I'm going to take a little pause and see if people have any questions. The first question that I want to ask is everybody comfortable with the sigma notation? Does everybody understand what the sigma notation is representing? Okay, we got a confirmation. Cool, cool. All right. All right, so if anyone is not comfortable with the sigma notation, but you don't want to post, in the text channel, you can always direct message me. I'm also paying attention to direct messages, but at this point, I only have confirmation, so I will assume that everybody understands the sigma notation. All right, but we also notice something that is not parameterized. See all these 10s over here? That's a literal constant, okay? So if these are all literal constants, that means, hey, what if we change this 10 to an 8, or we change it to a 16? Well, now we have a number that is in a different base, okay? That's basically what the base is when we talk about numbers, is we are raising, to which number to the power of 1 to -1 and so on. That is what the base is. So that means we can, instead of using base 10, we can choose another base. Okay, we can choose base 2, which is binary, and you can probably imagine why binary numbers are particularly important in digital computers that we use today. So that's kind of cool. We can also kind of imagine why base 16 may be really useful, because hey, instead of writing a whole bunch of zeros and ones, we can pack those zeros and ones into groups of 4, and each group of 4 corresponds to one hexadecimal or base 16 digit, so it's a lot more compact. But what about base 7? Can we have base 7 numbers? I don't see why not. Can we have base 3 numbers? I don't see why not. Can we have base 11 numbers? I don't see why not either. Okay, so we can use just about any any positive integer that is greater than 2 as a base. So we can now start to talk about base conversion. Okay, so let's talk about this equation here first. Okay, the only difference between this equation and this one over here, or the two formulae, is instead of using 10 as a literal constant, I just generalize it and go like, we'll just pick whatever base we want to use. Okay, b is the base that we're using. That's the only difference. All right, so now we'll start to get into base conversion. Which is basically saying, given this particular value, okay, what does it look like when it is represented by a number in base b? Okay, that's kind of the question we want to ask. So to some people, this may seem like a very difficult process, but we have done something that's far more challenging than base conversion already, and we can now do it on a daily basis without really having to think about it too much. Okay, so let me tell you what I'm referring to. And let me go back to my text window here, which is one. There we go. Okay, I'm going to use exactly the same text file. I can upload it again later. It's okay. Let's talk about currency. Okay, so let's talk about I'll just pick like maybe $17.55. Let's make it kind of more interesting. Let's say 62 cents. There we go. Okay, so let's talk about $17.62. And let's just say that we're let's say the tech picked up a job at McDonald's, okay? And I need to learn how to make an exact change of $17.62. Okay, that's my job, is to make change. Okay, can we do this? Do we know how to do this? I'm gonna guess, the whole class is gonna implicitly saying, yeah, we know how to do this. I mean, we're college students. Of course, we know how to do this. Even high school students can do it. Even some elementary school students can do it. Okay, and when I say do it, I mean, don't give the customer 1,762 pennies. I want to give the least number of coins and bills to the customer. Do we know how to do that? Okay, from the lack of response here, I'm going to guess yes. Okay, all right. So how do we do this? Well, we start with the $17, right? We say, well, there's $110 in that. Okay, so once we take off the $10, we have $7.62 left. And of that amount, we just say, we can use a 5 for that to take care of the 5. Now we have $2.62 left. So for the $2, yes, I do know that $2 bills exist, but they're very uncommon. So we'll just say that most people would use two $1 bills. I'm gonna use the quantity over here: one $10 bill, one $5 bill, two $1 bills. Okay. So now we have taken care of the $17. We only got 62 cents left. So of the 62 cents, I know we have half dollars, okay, but they're very uncommon, so we'll just use quarters instead. So we have 2 quarters, and once we take care of the 2 quarters, we have 12 cents left. Of the 12 cents, we can take care of the 10 using a dime. Okay, so we have 1 dime, and now we have 2 pennies left. So 2x, pennies, like that. There we go. I know most of you can figure this out like in seconds. You don't even need a piece of paper to figure this out, right? That is a lot more complex than base conversion already. In other words, you already know how to do base conversion. You just have to relate something that you can do really, really well already to base conversion. Okay, that's how I like to approach things, is to relate something that seems to be kind of difficult to something that you already know how to do. Okay, now why is this difficult? Because let's just look at the denomination of currency in the United States and see how they relate to the next level. So at the lowest level, we have a penny. Okay, the next level, we got a nickel, which is 5 times the value of a penny. And then at the next level, we have a dime, which is 2x the value of a nickel. And then guess what? The next level is a quarter, which is not even an integer multiplier compared to the previous value, because it's 2.5 of a dime. Okay, and then what do we have? We have a dollar, and which is 4 times the value of a quarter. You can see how the multipliers up to this point has not even repeated itself. We got 5, 2, 2.5, and then a 4. I mean, what the heck is going on here? Then we have a 5. Okay, so using this, if we were to introduce the currency, the U.S. currency system, to an alien, okay, coming from outer space, the alien would probably say, oh, the next one has got to be a $10 bill, because we are just repeating the 5 to 2.5 and the 4x pattern, right? So it seems, right, okay, that's good. So the next one is going to be 2.5, which means we have a $25 bill. No, we do not have a $25 bill. We have a $20 bill, which is another 2x. Okay, And then we have a 2.5 because we have a $50 bill at this point. And then we have, $100 bills, which is another 2x. You can see how this can be really confusing to an alien from outer space who is very, very good at math, because there's nothing regular about this. There's no pattern to it, okay? Things seems to be kind of random and kind of like, why do we choose this? Why do we choose this particular pattern, right? It's convention. It's really just convention. There are no good reasons of doing this. All right? So are we still doing okay so far with this particular example? Making an exact change for $17.62. Or is everybody falling asleep? Because I know how to do this already. This has nothing to do with assembly language programming. I am going to go back to sleep now. Okay, so we got some confirmation. At least one person is awake. That's good. All right, so now what we'll do is we look at a slightly different value. Let's say we're looking at $17 and let me see how to say this, $17.625, okay? But this time the currency system is a little bit different, okay? So with the new currency system, the alien or tax, currency system, we got a dollar. Okay, on one side we have $2, and then we got $4. These are the denominations. Okay, we got 8, we got 16, whoops, and then we got 32s and so on. But when you want to look at the coins, okay, we have a half dollar, and then we have a $quarter, okay. And then the next one down to us looks kind of really odd is an $1/8. Okay, so let's just say that I have just completely changed the currency system, to guess what? Powers of 2. Okay, now how do I make a change for $17.625? We say, well, we got one of the 16s. Okay. But once we take off the 16, we don't need the 8, we don't need the 4, we don't need the 2, because we only got one left. So we have one of the $1 bills. So once we take care of the integer part of the change, we have 0.625 left. Okay, so we ask, do we have a half dollar in that? Yep, there's exactly one half dollar. Then we don't need a quarter, because we can now just go like, well, what is left is just 1/8 of a dollar. So we go for the 1/8 of a dollar, and there's one of those. Okay, so that's just a kind of quick and easy conversion from a certain currency amount, which is 17.625 to the amount of bills and coins in the new currency system. Now, what I did not specify here is kind of the useless items, okay? Because we have none of the 8s, right? We have none of the 4s. Whoops. None of the 4s. We have none of the 2s, okay? So we have none of the 2s. And then on the other side, we have none of the quarters, okay? None of the quarters. There we go. Okay. So we look at this, okay, and then what we do is we say, well, we'll just pick up, the quantities, okay. So we got 1 of the 16s, 0s of the 8, 0 of the 4, 0 of the 2, 1 of the 1, 1 of the half, none of the quarter, and 1 of the 1/8. Okay. Does that start to look like a binary number to you? Certainly does to me. So now the question is, where do I put the point? Because I know we need a point somewhere, right? So the point is always to the right hand side of the digit that tells us the number of units, the number of the base to the power of zeros. So that means the point is going to be right there. So now we can now say, hey, this is a binary number. 10001.101 is expressing 17.625 as a binary number. Are we doing okay so far? Are we kind of relating um, what we understand about base 10 numbers, what we understand about the currency system, and just make a slight change to the currency system to relate it to base 2. All right, cool. This is nice. Cool. All right, so this is really kind of this is really nice. So now the question is, well, base 2 is kind of easy. Okay, base 2 is really easy because you either have one or none of a particular power of 2. That is why it is really so cool, because the conversion process is a simple comparison. Okay, if it's greater than or equal to a power of 2, we got one of those. If not, we got none of that. Oh, thank you. Thank you, Justin. So now we ask another question. We ask another question is, what about those really strange bases that I have just mentioned? What about base 7? Okay, how do we deal with base 7? So we'll come up with a number here. So let's say we're dealing with 497, okay, which is base 10. If I don't specify a base, it's base 10. So I want to represent this in base 7. Okay, what does it look like in base 7? So what would be helpful in this case is to kind of list out all the powers of 7. So we have 1, which is 7 to the power of 0. We have 7, which is 7 to the power of 1. We have 49, which is 7 to the power of 2. And then 49 times 7 is 343. 343. Let me double check. My arithmetic is really bad. Oh, okay. Thank you, Zach. Okay. So I think that's enough for what we need to do, right? Okay. So now we say, let's take a look at 497 as a base 10 number. It has got one of, the 7 to the power of 3. Okay. So once we take care of that, we have 154 left. So now we say, well, what about that? So we look at 154 and ask, does it contain any 49s? So it does look like it contains a few 49s. I think it has 3 of those, right? So we have 3 of the 49s, but each 49 is 7 to the power of 2. So now we have to look at what is left. So 3 times 49 is 147. Yep, thank you. So we subtract 147 from 154, we got a 7 left. So that is just completely coincidental. Yep. So now we look at this and go like, okay, that's an easy one. Because now we say there's 1 of 7 to the power of 3, which is 343. There are 3 of 7 to the power of 2, which is 49. And guess what? There's only 1 of 7 to the power of 1, because that's just 7 itself, right? And there's 0 of 7 to the power of 0. Okay? So once again, we have now figured out the quantities of each power of 7. Okay? So now we can say, oh, okay, so a shorthand to write out this expansion based on the powers of 7 is 1, 3, 1, 0 in base 7. So is that okay so far? So we can do base conversion to just about any base we want to use. even I think even if the base itself is irrational, an irrational number, we can still do it. It's just that to most values will now need an infinite number of digits to represent exactly, but it is still possible. Isn't that cool? All right. So, what does that have anything to do with us? Okay, so there are a few people typing, so I'm gonna wait until we got those questions. Cool example. Well, thank you. And we got one person still typing. How are we going to know it's 3 or 4 digits? Well, we just have to keep going in terms of increasing the power until it seems to make sense. It's okay to overshoot. If we overshoot, we simply have leading zeros on the left hand side of a number, which is okay. We just don't want to undershoot so that the quantity is more than the base itself. It's at least the base itself. Yep, we just add zeros to the left hand side. So it's always okay to overshoot. Why what? You mean why we are adding digits to the left hand side? So assuming that is the no on the right hand side, well, you can always add more digits to the right hand side, but you have to be careful about the point. Because in this particular example, okay, we can always say that there's none of 32. So that means the none of 32 is adding a 0 to the left hand side, right? But if you want to say we have none of the 16th, okay, a 16th I think is 0.625, 0.0625, then we are adding a 0 to the right hand side. Are we still doing okay? Thank you, Richard, for explaining that. All right. So I'm gonna assume that we are doing okay with this concept. Oh, okay. I'm gonna wait. Okay, we're good. All right. So now the question is, if I give you a value, how do you figure out, the representation in a particular base? So these are all just the derivations. This is the bottom line, okay? So the bottom line is, if V is representing a value, and I want you to represent that value in base B, then the ith digit, okay, which is what D of I is representing, can now be computed using just this equation over here. This really weird symbol over here is the floor symbol, okay? Okay, in the video I can show you right there. So it is this particular symbol is really the floor symbol, which is the floor of 2 point something is 2, the floor of 3 point something is 3. So it's kind of like truncation. It's not exactly truncation because it works differently compared to truncation for negative numbers. So as long as we're dealing with non-negative values v, you can look at the floor function as a truncation. Okay, we just get rid of anything that is not an integer. But that's the bottom line. Okay, let's see if this works, right? Because we want to test this. Okay, does it work? So we go back to an example that we have. Let's say the base 7 example. Okay, so we look at the base 7 example. Okay, okay, I'm just making some spaces over here. So if we look at the base 7 example and we say, well, let's look at D2, okay? D1, excuse me. D1 is referring to this 9 over here. No, excuse me. So D1 is referring to this 1 over here, the one that I have just highlighted. That's D1 because the 0 is D0, okay? Because it is representing the number or the quantities of 7 to the power 0. So let's see if this works, okay? We just plug in the value. So we are looking at the floor of 497 divided by 7, which is our base, to the power of I, which is 1 in this case. So once we have this, we want to mod it with b, which is 7. Okay, so let's carry out this math here over here. So we have 497 divided by 7. Oops. You cannot see it because I am using a calculator off screen. So we got 71 mod 7, and 71 mod 7 is just 1, because 71 is 7 times 10 plus 1. The 1 is the remainder. So that's why 71 mod 7 is just 1. Hey, that works out. What about D2? Okay, so D2 is the floor of 497 divided by 7 to the power of 2. Okay, and then mod 7. So the floor comes out to, just doing this off the screen, comes out to 10. So we got 10 mod 7, and 10 mod 7 is 3, because 3 is the remainder of 10 divided by 7. Hey, that works out too. So this is a really useful kind of little equation over here. If you want to figure out a particular digit of a number representing a specific value. Okay, so shall we move on? Are we good so far? I'm looking at the time. We got a few more minutes left. All right. All right, so we got one confirmation. What about hexadecimal? Oh, that's a good question. So let's talk about hexadecimal just a little bit, okay? So let's say in base 16, because hexadecimal, the hexa is 6, right? Deci is 10, so hexadecimal is 16. So it's basically base 16. So let's try to figure out D1 in base 16 of the same value that we're dealing with. So now we look at the floor of 497 divided by 16 to the power of 1. And then we take the result of the division and the floor and then mod with the base, which is 16. So I'm doing this off the screen. We have 497 divided by 16, which is 31. So 31 mod 16 is 15. Okay? Then we go like, uh-oh, we have a problem because D1 is 15. It itself has more than 1 digits. That's okay. It's not a problem because that is just the hexadecimal digit of F. Because in hexadecimal or in base 16, we basically reuse all the digits that we already have in base 10. So that goes from 0 to 9. But we also have to represent what we know as 10 as a single digit. So we start to borrow letters from the alphabet. So A is representing 10, B is representing 11. So when you extend it out, the last digit in base 16 is going to be F. So the single digit F in hexadecimal is representing what we know as 15 in base 10. So I hope that answers Catherine's question, at least in a nutshell. We're going to come back and look at hexadecimal numbers again, actually over and over again in this class. All right, cool. So section 6 is basically saying, what about base 2 or binary numbers? Well, that's easy because now we already know how to deal with base conversion to any base. Just tell me what B is and I can convert to that base. So in the case of a binary number, it just means B equals 2. Okay, that's really easy, right? But binary numbers are also special because there are only 2 possibilities to each digit. It's either a 0 or a 1. And it's also special in a different way because we already have ways, physical ways to represent a 0. Okay, if the voltage is below a certain threshold, I'll look at this as a 0. If a voltage is above a certain threshold, I'm going to look at that as a 1. So we know how to equate physical quantities to zeros and ones. But more than that, we also have certain operations that we can do to those voltages. We have that NAND2 thing, right? The NAND2 gate earlier. But you will say, but that's not a arithmetic operation, right? Because that's just a logical operation. What happens if we want to add or subtract values? So those are all very good questions. Um, so we'll talk about those questions. Okay, how do we add and how do we subtract binary numbers? But that's the next module. Um, why how are values represented in the computer? We just talked about that. But that's actually something that you don't get to see in C and C++, because most people, when they specify an integer constant in C or C++, they still use base 10 numbers, right? Um, and that is actually translated into base 2 by the compiler before that value is utilized in the program. So we are actually using binary numbers all the time, even in C and C++. It's just that the compiler is doing the job of converting a base 10 number into the base 2 representation before it is stored in instructions or before it's initialized in the memory space. Okay, there's an exercise to write a program to do base conversion. So we'll deal with that maybe at some other time. Okay, if anything, this is going to be an ungraded assignment because it does take a bit of time to write programs like this, and we are in a very compressed schedule. So that may not be a very good idea to kind of continuously give you guys the ungraded assignments. All right, so we are done with another module. So if we go back to the list of all the modules, the next topic we'll be talking about is binary number addition. Okay, we are out of time today. We got 3 minutes left, and I have to tell you what is the access code to the new lab for today. So we're gonna have to do that. But in terms of reading, hopefully before tomorrow, okay? So hopefully you can read this particular module, which is binary number addition, before we talk about this tomorrow at 9 a.m. And you can use the daily log to write down questions. In other words, you're reading this module and go like, I'm not really sure what you mean by carry look ahead. Okay, that's a term that you will see in this particular module. So if you're not sure and you say, okay, let me just listen to the lecture. If I'm not getting the meaning of that in the lecture, I want to ask it during the synchronous session. So use that daily log for stuff like that. Okay, so this way you don't forget to ask a particular question as you're reading the text. So as promised, okay, I'm going to open up this NAND2 lab, which is a really simple one. It's only worth like 4 points, but it will help you, one, get used to Logisim, and two, it will also help you start to kind of, by doing stuff like this, you will start to have an association of all the concepts, not only conceptually at a high level, but you're also doing it inside Logisim, so that will give you another pathway to connect all the concepts together. So I'm gonna just release this. I think most people would not have to spend too much time on this one. And I'll make it due tomorrow, which is June 10th. At 9 a.m. and June 10th at 9 a.m. And then the access code is Nandroid. N-A-N-D, Nand, Roid, R-O-I-D. So I'm going to write it in today's text channel over here. The passcode to the lab is Nandroid. The reason why I name it Nandroid is because I think the semester when I came up with these labs, I was also teaching an Android programming class. So I just kind of, in my head, everything is just a big, huge mixture of stuff. So I just go like, hey, I can come up with this name, Nandroid. Sounds kind of cool. There we go. So the lab access code is now on Discord, and it is also pinned. So this way, when people need to go find it, it's relatively easy to find it. All right, so we are out of time for the lecture. So let's go ahead and take a 10-minute break. I'll be back at about 10:30, but then I have to spend about 15 minutes, in the vehicle, so I won't be able to do a whole lot of interaction for about 15 minutes, but I'll be there. I can answer questions for the rest of the duration all the way to 1 p.m. All right. So I'm gonna check out right now,